In this video, I would like to work through and explain the multiple choice questions on this set of electrochemistry practice questions that I've just recently added, and kind of give you some of the background that might help you think some of these through. I don't know how many I'll get through in this first video, but we'll see how many we can accomplish before the video gets a little bit too long. And we'll take it from there. So this first one obviously is about electrolysis, and there's some simple numbers here as far as mental math goes to draw your attention to. This 243 grams, when we're talking about magnesium, you'd want to look at your periodic table and recognize that that's 10 moles. So 10 moles of magnesium have been produced. And to make 10 moles of magnesium would require 20 moles of electrons, because it's a 2-to-1 ratio in the half reaction. So we're thinking about magnesium 2+, requiring 2 electrons to form magnesium plain metal. The difference is that aluminum would require 3. So aluminum, to come from the aluminum chloride here, would require 3 moles of electrons to form the aluminum metal. And so the ratio there is 3-2. The 20 moles of electrons that you'd have to produce 10 moles of magnesium wouldn't be able to accomplish the same thing for aluminum, because it's going to take more electrons for every mole. And so you're only going to get 2/3 as much. You're only going to get 2/3 as many moles. So 10 moles of magnesium is 243 grams. 10 moles of aluminum would be, if you go to the periodic table, a mole is 27 grams. That'd be 270 grams. But you're only going to get 2/3 of that because of this 2-to-3 ratio in the electron ratios in the two half reactions. So 2/3 of 270 is 180 grams. So we'll get 180 grams of aluminum on that one. Okay. You could do it by a kind of a quick stoich too, but and relating those two things by 2-to-3 ratio, but it's a little tricky since they're not really in the same chemical reaction to think about that ratio as instantly. So just to recognize some simple numbers, in this case 10 moles of magnesium, how much would 10 moles of aluminum be, and the fact that we're not going to get quite as much because aluminum needs more electrons for every mole to be formed. For 2, this is a quick one, hopefully. When we have a positive voltage, so greater than 0, if E naught is positive, that means it's a spontaneous voltage, a galvanic cell, and that's going to be a spontaneous reaction. So we're looking for a G that's negative and a K that's very large. And so we want a G that's less than 0 and a K that's big. We're looking then at choice A. For 3, this question we looked at today in class as I record this, and in one class at least we discovered that there's a little bit of ambiguity here. So we're going to skip this one, and I've pulled it off of the original that was posted online. Many of you may have downloaded a copy and have this question, yet I've pulled the answer as well. It's a little bit ambiguous the way that it's written, and there's actually a few correct answers. Until I get some clarification, we're going to call that one as pulled. And not worry about that one. Number 4, we have magnesium and silver in a galvanic cell with a positive voltage 3.17. So that's quite spontaneous. Silver is readily reduced, even with a positive voltage, and the magnesium is a very active metal. So we get a big voltage here. The observed values it says here is 3 volts here in a cell where something's been changed. Okay, so what must have been the result, or what statement applies to this particular cell? So which of these things is true that would bring about a voltage less than the standard? And I want to point out here that this question is, I think, a little sloppy in that the standard voltage is 3.17 volts. Here they're still using that little naught symbol to talk about the voltage in this new cell built from magnesium and silver. That would no longer be accurate. So we're not going to have an E naught here if we're not talking about standard 3.17 volts. So that, truthfully, that little naught symbol wouldn't even be appropriate anymore, because we're not looking at standard conditions. Something's been changed. Because it's standard conditions, we'd have 3.17 volts, and apparently something's been changed to alter that case and give us only 3. What might that have been? Is kind of what the question's asking. Well, to decrease the voltage, we'd have to either reduce the amount of silver. That would reduce the driving force of the reaction and decrease the voltage of the cell, or increase the magnesium ion concentration, which again would sort of prohibit or inhibit the forward reaction and reduce the driving force of the reaction that would power the cell. So that's a couple ways to do it. So which of these options accomplishes that? The addition in option 1 here, the addition of more oxidizing agent would increase the value of E. Well, that's not what's going on here. We're not increasing the value of E, but is that true for the cell as described? What is the oxidizing agent? So when we look at oxidizing agent, remember that's the species being reduced. What's being reduced by this reaction or in this reaction? And the silver is what's being reduced from 1 plus to 0. So if we were to add more silver, would that increase the value of the E? Yes, it would. It would increase it to something greater than 3.17. That's not the scenario what's been given in this question, where the voltage is described as being less. However, it is true that the addition of more of the oxidizing agent, more of the silver ion, would in fact enhance or increase the value of E. So that's true. What about number 2? The addition of products would decrease the value of the standard cell voltage, and that's the key to throwing out option 2. We can't decrease the value of the standard cell. That's a constant. If we're talking about standard conditions, the value of E naught is 3.17 volts, and that's kind of what we mentioned to start this question. By discarding that naught symbol, we're no longer talking about standard conditions. So this is a constant at standard conditions. And so the question sort of moot here in question option number 2 is something we can sort of throw out right away just on face value, because if we add products, in this case that would be the magnesium, then we're no longer at standard conditions, because now magnesium would be greater than 1 molar, and so this is out. That's not even a possibility. 3, as this reaction proceeds, the value of E will decrease and the value of E naught will remain the same. Well, that's very true. Value of E naught will remain the same is true, because it's a constant value, as we just mentioned. And as this reaction occurs, will the cell's voltage decrease? And the answer is yes. Make sure we understand why. If we look at this reaction, what will naturally happen as this cell proceeds is the silver concentration will decrease because it will be used up, right? The silver will be decreased at the cathode cell, or in the cathode half cell, and the magnesium concentration will increase in the anode half cell. So both of these things will be happening naturally as the cell, each half cell and the combined cell overall proceeds. So yes, in fact, as the reaction proceeds, the cell voltage will decrease while the value of E naught will remain the same. So 1 and 3 are both correct. That gives us our choices as letter C. Number 5, which of the following is a redox reaction? We're looking for an equation in which some oxidation numbers are changing. All right. So in which case is that the case? If you look through here, letter A is a simple double replacement reaction. It's a neutralization of a strong base, strong acid. Nothing's changing oxidation numbers. You can go through and assign everything, but everything remains the same. On letter B, lead is a 2+ ion at the beginning, and it's still a 2+ in that lead chloride at the end. So no change. This is still 2+. This is still 1-. So nothing's changed there. Letter C is a precipitation reaction between silver nitrate and hydrochloric acid. Again, everything's charge has stayed the same, including our nitrogen at 5+ in there, which is often something we recognize as being reduced in a case like this, but it's not happening here. It's still 5+. So in truth, none of these is a redox reaction. All of these are either double replacement reactions or a net ionic equation, in the case of letter B, that's probably from a double replacement reaction where the lead chloride precipitate is being formed. On number 7, we've got the 2 half reactions. These 2 half reactions are being combined to yield this overall net reaction. And so the question becomes then, how are we going to piece these 2 together to form the original reaction at the top? And then they want to know what's the reduction potential for this particular half reaction that they've given us here isolated at the bottom. And of course, that's the same as this one right here. So they're asking us for that. And it's showing the reduction, in this case, of oxygen from, in the first part of the reaction, oxygen is 0, and by the end it has a charge of -1 in the peroxide ion. So what is the reduction potential for that equation as it's written? Now the trick, of course, with most of these is that in order to create that reaction as shown at the top, overall we're going to need to flip the second reaction equation. All right, so we'll take this second equation and reverse it. And then in doing so, we'll need to reverse or flip the sign on our voltage as well. So if we reverse this, right, we'll have H2O2 yielding O2 plus 2 hydrogens plus 2 electrons. And if we keep the first equation as written, we have O2 plus 4 hydrogens plus 4 electrons. yields 2 waters. Now, these equations don't go together quite perfectly because we need to balance them with respect to electrons. And so we'll need to double our first equation, which is fine. 2, 2, go 4 of those and 4 of those. Let me try cleaning that up a little bit better for you. My apologies. That was kind of sloppy on my part. We've got, again here, 4 and 4. And then our electrons will cancel out. When we merge these together, our hydrogen ions will also cancel out. Our oxygens, this one will cancel one of these. And our bottom line then is, as the equation is written, 2H2O2 plus, yields oxygen plus 2 H2Os. And that's our overall reaction equation that's given at the top. So what would the voltages need to be for that to be the case? Well, we used this first equation here as it's written at 1.23 volts. We know the overall net voltage is 0.55 volts, which means the voltage here would need to be negative 0.68 volts in order to make that add up properly. Now that answer's there in choice B, but of course, remember, we flipped this equation. This is the, if we look at it, oxidation potential for that reaction. And so in order to kind of get back here to the reduction potential, we need to flip it back again, and that gives us positive 0.68 volts. So our bottom line answer there is letter C. Okay. On number 8, which gives the changes in masses of the electrodes that occur in operation of the cell. So both of these half reactions show the reduction of silver and of iron respectively. We're not going to be able to use both of those as is. But remember, voltaic cell means we need a positive voltage greater than 0. So in order to combine these two, we're going to need to flip the second one. So we're going to keep this one as it's written, the first one, but we're going to flip the second one. And so we'll use the first one like it is, and then flipping the second one gives us iron becoming iron ion and releasing 2 electrons with a positive 44 volts. All right, so which of these is happening where? Well, we have oxidation of the iron, so this is happening at the anode. Oops, pardon me. Let's try that again. It's happening at the anode. The silver reduction is happening at the cathode. And then, as we know, anodes get thinner or lose mass, and the cathodes gain mass. So our silver is going to increase in mass. Our anode is going to decrease in mass. So silver increases, that's here and here. And iron decreases, that's here. And so our choice must be B on that question number 8. On to number 9. Which of the following reactions will occur spontaneously as written? We're looking for a positive voltage, right? So again, E cell greater than 0 for the overall cell. When we combine two of those, it's important to note, though, that a couple of these options show reduction on both parts. So on choice A, we have tin being reduced from 4 to 2 and iron being reduced from 3 to 2. We can't do that all at once, so that's out. We can't have 2 half reactions happening at once. The same thing can be said about letter C, where tin is going from 4 to 2 and iron's going from 2 to 0. So that's reduction. Not going to work. So we're down to 2 just like that. And then we go up to our choices at the top and pick out the ones that show, when combined, a positive voltage. Well, letter B is using iron going from 0 to 2, so that would be using this one flipped, positive 0.44. And it's showing chromium going from 3 plus to 0. Now that's given as it is up here, so that's negative 0.74. And together those would make a negative voltage, negative 0.3. So that's not going to work. That's a negative 0.3 volts. So that's out. That's not a spontaneous galvanic or voltaic cell. Let's make sure D is. D would have tin being reduced from 4 to 2. So we're going to use that last equation as it's written. And it shows chromium going from 0 to 3 plus. So that means flipping this first equation to a positive 0.74 volts. And if we combine a positive with a positive, we get a positive. And so question number 9 is D. On number 10, based on the standard potentials given, which is the strongest reducing agent? I think I mentioned that nowadays they're not going to ask you about agents very much as a content idea, but it's helpful, I think, to understand what the heck reducing agent means. So strongest reducing agent Remember, the opposite is true of what's happening to that atom or that particle then. The reducing agent is itself being oxidized. So strongest reducing agent can be translated as which of the following is the best or most spontaneous at being oxidized according to the voltages. So in being oxidized, which has the greatest, most positive half cell voltage? And so based on what's given here, cadmium, to show cadmium being oxidized would be to look at that first equation and flip it. That's positive 0.41 volts. For CD, for cadmium 2 ion to be oxidized, we really don't have an equation that shows that. So we don't have information for that. But it's safe to say that because oxidation is the loss of electrons, and since cadmium has already lost 2 electrons to reach cadmium 2+, that it's not going to be very spontaneous to lose additional electrons. Even 1 would be very unfavorable. So to lose a third electron for cadmium here is unlikely. Very, very unspontaneous, very not favorable in terms of that voltage. So we're going to take that one out. Copper, as it's written up here, copper, if we had to flip this equation now to show copper being oxidized to a 1+, it would have a negative 0.52 voltage. That's not real spontaneous, certainly not as spontaneous as is choice A. And silver being reduced, according to that last equation, being oxidized, as we mentioned with cadmium, to lose another electron from silver +1, which already has lost an electron. And silver +1 is sort of the stable form of the silver ion. To lose another electron is thermodynamically highly, highly unlikely. So out. Most positive one then is letter A. The most likely to be oxidized, according to the data that we have here, is the cadmium atom. To form the cadmium ion, a positive voltage of 0.41 volts. So for 10, we got A. 11 is another one that's balanced in basic solution. So I'm going to leave that one out because we're no longer doing acidic basic, balancing in acidic and basic environments from half reactions. I'm going to pull that one out. Okay, so we'll skip over that one. 12. In the reaction shown, the number of permanganate ions that react must be equal to which of the following? So we're looking for ratios here. They've got various ratios. A, 1/5 the number of iron 2s that are consumed. And that's the answer right off the bat, because there's 1 part permanganate ion for every 5 parts of the iron 2. So that's correct. A. We can take a look real quickly at the other ones. 8 times the number of hydrogen ions? Nope, it'd be 1/8 the number of hydrogens being consumed, because 1 of these for every 8 of these. So that's 1/8, not 8 times. Iron is being produced. Again, that would be 1/5, not 5 times, but 1/5. And 1/2 the number of oxygen molecules produced, it'd be 1/4 because of the 1:4 ratio. So the only one that actually fits those given is letter A. And that one hopefully would be pretty easy if we ran into that one in a dark alley or on the exam. 13. When a magnesium wire is dipped in a solution of lead nitrate, a black deposit forms. Which of the following can be concluded? Well, think about that. What's happening there? Magnesium is going from magnesium to magnesium 2+ by losing electrons. And lead, right, which in lead 2 nitrate is lead +2, is gaining 2 electrons to become lead metal. And that's what that black stuff is. Black deposit is the lead that's being formed as a solid on the strip of solid magnesium, coating it. It almost looks like kind of like a black mold almost on there when it does that. It builds up rather quickly. But what does that mean for us? Well, this is a spontaneous process. So together, these two both have a positive voltage. And so magnesium is being oxidized. Lead is being reduced, and quite spontaneously. So the very first choice here says the standard reduction potential for lead 2 is greater than for magnesium 2. Well, think about that. It would have to be that, right? Because the reduction potential for the second reaction equation, let's say it's positive 0.5. I don't know what these numbers are, but we don't need the numbers to solve it. If for the first part, for the magnesium half reaction, its reduction potential would have to be something less than that. So the original equation, just to try to kind of compare, the reduction equation for magnesium would look like this. Magnesium plus 2 electrons becoming magnesium. And that would maybe, let's say that one's even a positive 0.3. As we flip it to make that equation that we actually used, we'd get negative 0.3, and that would still allow this to be a positive overall E cell. No matter what, that has to be the case, right? Because if this wasn't the case, and let's just say, for example, that magnesium's original reduction potential was, instead of positive 0.8, let's say positive 0.7. When we flipped it to put those two together, it becomes a negative 0.7. And now this would be a negative overall, and that would not create a spontaneous result. So the very first one they gave us here is true. It has to be the case that the standard reduction potential for lead is greater or more positive than it is for magnesium. And we've picked just some simple numbers to kind of prove it for ourselves, but that's the case. Having a greater standard reduction potential means that when you put these two things together, the one that has the greater standard reduction potential is the one that will be reduced. And so the case as it is, and again, let's switch it back to the numbers that I'd thrown up originally here as a 0.3 and a 0.3. And then we'd have an overall positive, like 0.2 volts. And again, these are just hypothetical numbers. If that's the case, then the more likely to be reduced is the lead, because 0.5 is greater than the original 0.3 for magnesium. So the greater the standard reduction potential, that's the one that's going to be reduced when you put them head to head, okay, as a pair, and potentially making a voltaic cell, as we've done here. Let's just check the other ones real quick. Magnesium solid is less easily oxidized than lead. Well, that can't be the case, because magnesium is very quickly being oxidized here. Think about, in this case, magnesium is more easily oxidized, because if we flip this bottom equation, we'd get an oxidation potential of negative 0.5, and that compares to magnesium at a negative 0.3. So magnesium isn't less easily oxidized, it's more easily oxidized. Because while it's negative, it's not as negative as it would have been for lead. An external source of potential must have been supplied? No, it's spontaneously happening. We dipped it in there and the deposit formed right away. So no additional voltage from the outside was needed. In fact, in the right conditions, we could make a positive voltage producing cell out of this. And then it says the magnesium ore with the cathode of such a cell. Well, no, the cathode is the thing that's gaining mass. And in this case, it'd be the lead that would be gaining mass. It's being reduced, and that would be happening at the cathode. So the magnesium would be the anode strip, and the lead wire or strip would have to be at the cathode position, not the magnesium. Okay. Let's keep on trucking. 14. There's a lot going on here, and I'm guessing, I'm not sure about this, but I'm guessing if this was ever actually used in a mock exam or an old real exam somewhere, that this information that you see given here before question 14 was probably used in several multiple choice questions, because there's far more information really here than we would need in order to answer the question that was given here for just number 14. So you've got a whole bunch of extra stuff, much of which you wouldn't even need in order to answer the questions that we're really using here. So they're saying that we're gonna switch out and use a half cell containing iron nitrate, which would be this one right here. Instead of using one that has 1 molar iron nitrate, what happened if we increased that iron concentration to 5 molar? So we're jacking up the concentration of iron. They're asking what will be the effect on the cell voltage of the two galvanic cells. And those two cells are being described, the ones that contained iron would be cells Y and Z. So galvanic cells Y and Z. We can leave out cell X here because that one doesn't involve iron at all. It wouldn't be affected. And so they're not even giving us any options about that one. So we can kind of forget that's even there. But what would happen in each of these other two cells? Well, as we increase the iron concentration, cell Y, the iron is a reactant. And so adding more iron would increase the driving force and would raise the voltage. Okay? It's probably quite a bit. And with 5 molar, that's a big increase. But on the second one here, on cell Z, the iron is a product in that reaction. And so adding more of the product ion will not favor the forward reaction, will not encourage the forward reaction. In fact, it would sort of discourage that forward reaction. And that would, that would decrease the voltage on the second cell. So it will increase in cell Y because we're increasing the driving force, and it will decrease in cell Z. So our answer here is letter C. All right. In 15, they want us just to pick from these which of these two half reactions are occurring in each one. Well, here's iron being oxidized from 2 to 3. So that's this guy here, or this one. Those are the two choices we've got. Oh, pardon me. We don't even have that many choices. We've got that one choice because that's the only one that's showing oxidation. This second equation here on letter C is showing the electron on the wrong side of the equation. So iron 2 would not gain an electron in order to become iron 3. It has to lose it. So this isn't even a feasible equation. It's not oxidation or reduction. It's nonsense, really. So we've only got one good choice. Is in fact this other equation what's going on for the reduction? Yes, cerium is becoming a 3+ from a 4+, and that happens by the gain of electrons. So that first equation works, and our answer is A. 16. When acidified potassium dichromate solution is added to sodium sulfide solution, green chromium 3+ ions and free sulfur are formed. When acidified potassium chromate is added to sodium chloride, no change occurs. Of the substances included in these reactions, what is the best reducing agent? Okay, so in other words, who's being oxidized? The best reducing agent. Who is being oxidized? That's really what the question's sort of asking. And one of the equations, or one of the scenarios as described, no change occurs. So it's pretty safe to assume that sodium chloride isn't really doing much of anything. It's not being oxidized or being reduced because nothing occurs when it's used. So I'm going to go ahead and throw that one out right away. Okay. What about the others? What's happening in that first scenario? To go from potassium, it's real close all of a sudden, to go from potassium dichromate, which a chromium has a 6+ charge in, to chromium 3+ here. That's reduction. So that's not what's being oxidized. That's what's being reduced. That makes this guy the oxidizing agent, but not what's being oxidized, not the reducing agent. So that one's out. And chromium, as a 3+ ion, is the product of this reaction. It's not a reactant. And remember, agents need to be from the left side of the equation. They need to be something that's put into the reaction, not something that's spit out of the reaction. So we can kind of rule out chromium 3+ as the answer too, because it's a product, not a reactant, and therefore it can't be one of the agents of the equation. So how can we prove then that sodium sulfide is in fact the reducing agent, or what's being oxidized? Well, sulfur is going in sodium sulfide from a 2- to sulfur-free sulfur as a 0, and so that's an oxidation. That's who's being oxidized. Therefore, that is the reducing agent. Not only is it the best reducing agent that's given here, it's the only one that's actually doing that job at all. For 16, we're looking at B. Okay, I'm going to do, I think, 2 more, maybe just this one more, and then we'll end this video and do the second part as a separate video. So just one more. The balanced half reaction must illustrate conservation of what? Okay, so looking at a balanced half reaction, what's a simple example of that? Well, we've been looking at them all over the place, but let's just do a real simple one. Here's copper gaining 2 electrons to become copper metal. Okay. Bad looking arrows there. Let's not mess with that. That's a balanced half reaction. Right? Simple as can be. What is it showing conservation of? Well, we have to have the same number of atoms when we balance these. So 1 copper atom and 1 copper atom. So yes, it balances the number of atoms. It shows conservation of charge because on the left side of the equation, if we add up all of our charges, we have a charge of 0. And over on the right side, we have an overall charge of 0. So that's true. This equation doesn't show any molecules. So apparently not every half reaction has to show conservation of molecules. And that is to say, we don't have to have the same number of molecules on both sides of the equation when we're balancing a half reaction. But let's take a quick peek at an equation that actually is involving molecules. So you can see that molecules aren't conserved. So a quick and easy one there is, let's take water and show water being reduced. So water being reduced, or specifically the hydrogen being reduced to hydrogen gas to form hydroxide ions. And since reduction is the gain of electrons, we need to show electrons over here. And so if we balance this whole equation out, right, we're going to have 2 of these. Right? We're going to have 2 of these. And I think as far as atoms now, we're good to go. Okay, so I've got 4 hydrogen atoms on the left. I've got 4 hydrogens on the right. I've got 2 oxygen atoms on the left. I've got 2 oxygens on the right. So we're still balancing this with respect to atoms. Charge, let's see, did we balance it with respect to charge? We haven't yet, but we will. We're going to need 2 electrons in order for that to happen. Now, this side adds up to -2, and this side adds up to -2 as well, right? 2 -1s. So we've balanced it with respect to charge. Have we balanced it with respect to molecules? No. In fact, here we have 2 molecules, and over here we have what amounts to 3. I mean, here's 1 hydrogen and here's 2 hydroxides. So this is 3, we'll say, molecules. One of them is kind of an ion, but it would still kind of count. And over here we have 2 molecules of water. So even if we wanted to be real, like strict about the definition of a molecule, truly then on the right side, the only molecule is the hydrogen molecule. And even then, we're not conserving it because we've got 2 molecules of water and only 1 molecule of hydrogen. So no matter how you slice it, molecules need not be conserved in an equation. They might be occasionally, but they don't have to be. And so that rules out molecules as a choice, and we've got charge and we've got atoms. So for 18, our answer is letter C. So I'll stop this video there, and I'll record a second one for items 19 through 35 and post that one right behind this one. Until I see you then, thanks for listening, and I'll talk to you in the next video. All right, let's pick up with the second half of these electrochemistry multiple choice questions, just on our walkthrough to work out most of the solutions and try to give you some background for anything that's confusing you yet. The previous video we went through question 18, so we pick up here with number 19. There are a couple of equations in this set that I'll be showing you, or questions rather, that I'll be showing you some balancing techniques for that we may or may not have covered in class to this point, and that you may or may not have to actually accomplish on the actual exam because there's some disagreement as to whether balancing equations in acidic and basic solutions is actually something that's going to be tested. But I think it's really helpful, and it's not so hard. So I will show you a couple on here, but if you feel a little puzzled about those as we reach them, for example, number 20 will be one like that, then talk to me individually or outside of this video, and I can help you out with any sticky points on those. On 19, though, it asks us to fill in the blank, and this is kind of unusual, actually, but it says the more blank the value of the reduction potential, the greater the driving force for reduction. Well, we've talked about this and seen this a lot. Positive potentials, whether they're oxidation or reduction, mean that there's something about them that has a significant driving force. The more positive a potential is, the more spontaneous or thermodynamically favorable that process will be. So the more positive the reduction potential, the more significant the driving force for that process will be. So that's A. For 20, as I mentioned, we're looking at one of these here where we're going to be balancing a reaction overall that, frankly, when it's written like this, is dang near impossible to write a balance. So we have to actually take it apart. And so what I want to do is pull out the parts that are being oxidized first, and I'll do those for you here in red. So we have zinc forming zinc ions. And then to do that, it needs to be balanced. Each of these half reactions should be balanced. And so we're missing some charges on this one, some electrons. So there are 2 electrons being released by this oxidation of zinc. Remember, oxidation is loss of electrons. In this case, the zinc is losing 2. Now, that doesn't mean we can jump in here and say, oh, this equation's balanced and zinc has 1 on it, so the coefficient for zinc will be 1. Well, that's not even one of the choices. So we're not quite done yet. We need to take the oxidation half reaction, or the reduction half reaction, and show the balance of that, and then combine the two. So the reduction in this equation, I'll do that in blue, the reduction is the nitrogen. This is a typo here, by the way. This should be NO3 -1. So that's the nitrate ion. So I'm just going to kind of fix that real quick, like. Should be like that guy. And as far as our oxidation numbers, nitrogen is going from 5+ here to 3- in the ammonium ion. So that's a pretty significant reduction. Significant or not, it's the reduction reaction. So what's going on here is we have nitrate containing nitrogen being reduced to, can't write an arrow today, being reduced to NH4 containing nitrogen. But that's not balanced, obviously, because there's a lot of things that are sort of goofy here. Like, where are those oxygens going? And the way we balance it is by showing those oxygens popping up in water molecules. Oops, I won't need to.
water molecules on the right side. And how many of them will it take? 3 water molecules to contain those 3 oxygens that we need to account for. So I need 3 water molecules. Now the other thing by doing that, we've added hydrogens as well. We've added 3 times 2, 6 hydrogens in those waters. Now we already had 4 hydrogens present in our ammonium ion. So we actually have on the right side of my equation now 10 hydrogens. So on the other side of the equation, I'm going to add those 10 hydrogens over here. So now my equation is at least balanced with respect to atoms. 10 hydrogens on either side, 1 nitrogen, and 3 oxygens on either side of the equation. But it's not balanced with respect to charge. And that's the important one to kind of do last here. If I take a look at it, on the left side of my equation, I have 10 plus and 1 minus. So on the left side of the equation, right here, right, I have 9 plus, like together. Now on the right side of the equation, I have just 1 plus altogether. So that's not balanced with respect to charge. As we've done before, we can only bring positives down when balancing with respect to charge because the only currency we have to balance these equations with respect to charge is the electrons. And so we can add electrons to the side where it's necessary. Remember, we're showing the reduction of nitrogen from 5 plus to 3 minus, remember. And that would require some electrons to do it. In fact, if you look at that, it would require 8 electrons. Right? To go from 5 plus to 3 negative would require 8 electrons. Well, it turns out that that's exactly the number of electrons that we needed to do this balancing of this equation, because now, if I clear this out, now the entire left side of my equation has 10 pluses in my hydrogens, and then 9 minus or 9 negative in my nitrate and my 8 electrons. So my left side is now 1 plus. So that equation is balanced with respect to atoms and with respect to charge. And that's what we need to have it be. Now, if we're to put these two these two equations together, we've written our reduction equation for the nitrogen and we've written our oxidation for the zinc. If we're to put these together, we need our electrons to be equal, right? So that they'll cancel out. So if I'm going to do that, I'll have to take my first equation, the zinc half reaction, and take everything times 4. So I need 4 of these, I need 4 of these, and I'll have 8 of those. Now I can put these together, and I won't do it, but you can see here that I would be able to merge these two equations, right? Put these two equations together, and the electrons would neatly cancel out, which is our usual goal. Nothing else would cancel out. Like everything else would still be there. And so in the end, it asks for the coefficient for zinc, and that's this guy right here. So our answer is 4. Now, as I said, this is balancing half reactions and then merging them back together in a process that we haven't necessarily hammered on in class too much, at least not in the year that I'm recording this video. And so if you like doing this, it's really super handy and super convenient to be able to use it when you get an equation like this, and it's not hard. So if you feel like this is something that you have a little bit of trouble with, certainly sit with me. I can work you through a bunch more of these and find out that they're not very difficult. We won't go into the ones where basic environments are necessary. That does add a whole new layer at the end, and I'm not going to do that with the multiple choice video here. If you're curious about that, I'm happy to show it to you. It adds a few more steps, but there will be one, I believe, later on in this set that has a basic environment, and we're not going to do that one. We're just going to skip it. The way I know this is an acidic environment, by the way, is because this equation involves these hydrogens in the left side of my reaction, and so that's a sign that we're working in an acidic environment. A basic environment would have hydroxide ions instead. Okay, let's look at 21. This question is a lot like one that was earlier in the packet where it talks about changes of mass. What would happen to each of these? Again, remember, we want to identify by putting these two together which electrode will be changing in which direction. And we're making the assumption here that we're talking about a galvanic cell. It doesn't really mention that, but to have the mass of lead and the mass of silver changing in this way, we wouldn't probably be doing it by electrolysis, in all likelihood, because there wouldn't be a solution necessarily that would contain both of these ions mixed all together. That would be a very realistic scenario. So we're looking at this as a voltaic cell, so we're going to need to flip one of these because both equations, as you see them here, show reduction. And so we'll flip the first one in order to get a positive overall voltage, and that'll give us lead being oxidized to lead 2 and releasing those 2 electrons. If that's the case, the lead is the solid here, and it's going to be losing mass, right? So lead will be turning from solid into ions. That means the lead's going to be losing mass. So that gives us the choice that we're looking for kind of right away. We got kind of lucky on that. And on the other side, the silver is going from ions here to solid here. So it's gaining mass, and that makes sense as well. All right, let's look at 22. What is the oxidizing agent? That's the thing being reduced. And we often find this with permanganate. There's manganese at 7 and there's manganese at 2. So this manganese is being significantly reduced. That makes the oxidizing agent the MnO4 ion. It's the thing that's being reduced. Or a bit more correctly, it's the molecule or ion that contains the element being reduced. In this case, that's the permanganate itself. Okay, the permanganate ion contains the particle that's being reduced. So we wouldn't say the manganese 7 is the oxidizing agent because manganese S7 doesn't exist on its own. It's part of the agent that contains it. So that's a little bit of a slight nuance there that maybe you didn't know. 23. Consider an electrochemical cell based on this reaction. We have the reduction of hydrogen going on, and we have the oxidation of tin. So the questions asking then, and this is careful, look for this warning word in our questions, right? Which of these actions would not change the cell potential? We don't know what it is. We don't know what the cell potential is, but it would be given over here if we had it. We don't care if it's positive or negative or how big it is. We're simply asking which of these would not change it. So which of these would not have an impact? Well, let's look at the questions, or the options rather. Lowering the pH in the cathode compartment. Remember, we said that the hydrogen here is being reduced. So hydrogen is becoming hydrogen gas, and to do that, it's gaining 2 electrons. That's our reduction half reaction. That's happening in the cathode compartment because that's where reduction occurs. Well, if we lower the pH, that means making it more acidic, right? So we would be adding more of these. Would that affect the reaction? Certainly. That would increase the driving force of the reduction half reaction and of the overall reaction up here. So that would change the potential. That's out. Would adding more tin metal to the anode compartment change things? Well, that's tin right here. And in the anode compartment, we have tin becoming tin ion and releasing its electrons. But here's that snag, right? Changing the amount of tin doesn't affect the potential of this cell. Now you might look at it and say, wait a second, why not? I'm adding something on the left. Why wouldn't that increase the driving force? But remember, when we're talking about these, whether we use the Nernst equation or we just think about it as K versus Q, which is the way to sort of evaluate these without using the Nernst equation fully, the only substances for whom changing the amounts or concentrations will matter are those things that show up in a K or Q expression. And since this is a solid, it wouldn't be part of the K or Q expression, and therefore would have no role in determining whether the voltage would change, whether the driving force would be affected. So that won't have an effect on the cell potential. So that's actually the correct answer. Let's just briefly make sure the other ones, though. We've ruled out B, so we can also rule out D, because any of the above will change when we say B won't. So that's not true. But for letter C, increasing the pressure of hydrogen gas in the cathode compartment, that would be raising this instead, right? Will that affect it? Certainly, because this is a gas, it will show up in the K expression, the Q expression, and that would be on the product side of the reaction, and therefore it'd be on the numerator in my K or Q expression. And it would then, if I increased the hydrogen gas pressure, it would affect the K, rather the Q, and it would affect the voltage. We don't have to get into how it would. It would decrease the voltage, but in this case, all they want to know is would it change it? And yes, it would. Therefore, it's not the answer to question 23. All right, let's go to 24. The spontaneous reaction that occurs, we've got a silver and cadmium galvanic cell with standard 1 molar solutions. They want to know which of the above occurs for the following circumstance. This is kind of weird. They're going to take the salt bridge, which of course we know is this guy right in here through the middle, right? And they're going to replace it with a platinum wire. Now we see a lot of times platinum wire, especially in redox reactions where there's electrolysis going on, and we need a place for the newly formed metal to build up or for the non-metal gas to bubble off of, or if we simply have ions changing charge without depositing or being oxidized and lost at all. So platinum wire is kind of a familiar character in our stories with electrochemistry. But if we put a wire in here instead of a salt bridge, what would happen? And it helps, of course, if we understand what the heck the purpose of the salt bridge is, which is to allow half cells to remain charge neutral. In other words, the salt bridge adds either cations, usually potassium, or anions, often nitrate, to the appropriate half cells. It allows for the flow of ions, cations and anions. a platinum wire cannot allow for the flow of cations and anions. It can only allow for the flow of electrons, which makes a platinum wire a great choice for up here in my wire, but a terrible choice for as a salt bridge, because it's not a salt bridge. It wouldn't allow anything to flow in terms of those cations and anions. So this whole thing would break down. The voltage would decrease, yes, but it would decrease to the point where it wouldn't work at all. This cell wouldn't work. So voltage becomes zero and stays at zero until you get your head straight and put that salt bridge back in there. Okay, 25 is probably the most challenging mental math in this set of questions. And that said, it's not brutal, but it is mental math that I know some of you maybe have a little bit stronger cards in than others. And so on this, you want to think about it maybe as a Stoic situation. Some of you are real savvy on an MV kind of equation, but that gets a little bit less consistent and predictable if you're not really good at those. So I'll work it out here as a stoichiometry question, just to kind of show you how you could work through it. They want us to take 14 milliliters of the permanganate and figure out the concentration of the iron. So we're relating those two species from this equation to each other by the Stoich. And I'm going to start with my 14 milliliters of the permanganate ions. And we don't want to start with this one because we don't know its molarity, so we wouldn't have anywhere to go with it. So that's what we're going to end working with. But we're going to start with 14 milliliters. So 14 milliliters of a 0.05 molar MnO4 solution, which would be 0.05 moles per 1,000 milliliters of solution. And then in the equation, we've got a 5-to-1 ratio. So if I'm working this out as kind of a stoichiometry conversion, in the equation, there's 1 mole of permanganate for every 5 moles of iron. In this case, iron 2+. And that's as far as we can go, because the next step would be to have knowledge of the moles per liter or moles per 1,000 milliliters for that iron solution. And that's what we're trying to figure out. So we can't go any further. So we have to stop right here and do the mental math and get the number of moles of the iron ion, and then we'll use that 25 last to finish this thing out. So as far as mental math goes here, how you'd go about this is sort of up to you, but I've got 14 times 0.05 times 5 divided by 1,000. That's kind of what that boils down to, right? Now I like to do this trick where I come in here and I see 5 times 5 as 25, but there's decimal points here, right? So 5 times 5 is 25, but I need to add these 2 decimal places back in. So that's essentially 14 times, I'm sorry, that's if it's 5 times 5, 25 would be 0.25. Okay, so that's this part, 14 times 0.25 so far. And 14 times 0.25, I think about that as 1/4 of 14, right? So half of 14 is 7. Half of that would be a fourth, is 3.5. So I have 3.5 over 1,000 here so far. So if I want to just leave it at that, I can. I could leave it at that, or I can go ahead and write it as 0.00123. Move the decimal 35 moles. Right? So divided by 1,000 means moving decimal 3 times, 0.0035 moles of Fe. Now, to figure out the concentration, we need moles per liter. So that many moles in a 25 milliliter sample, right? So 25 milliliters in liters is 0.025 liters. And so to do that mental math with that, let's get rid of all those honking decimal points. Let's move things over. So I'm going to move over 1, 2, 3, 1, 2, 3. I've got 3.5 over 25. That's what that comes out to be, right? And as far as doing the mental math, then from there, 3.5 over 25 would be what over 100? That's kind of an easy way to think about that. Well, I'm taking this times 4, so I have to take this times 4, and 3.5 times 4 takes me back to 14. 14 over 100 is 0.14. So 0.14 molar is the answer, and that's our D right down here. Okay. Let's look at 26. Ionic species found in the half cell contain the cathode. So we want to identify, if we can, looking at these 2 half reactions, what's being reduced? What's the reduction reaction, right? So we've got 2 reduction reactions given, and we're going to need to flip one. We're going to assume again that we're working with a galvanic cell. So we're going to need to flip one that will allow us to have a positive sum when putting those together then. So obviously we're going to flip our first reaction to make that a positive 0.76. And if that's the case, then which reaction will show reduction? Well, it'll be this one, right? This is reduction. It'll stay as is. The top reaction when flipped will show oxidation, and we're looking for the cathode's reaction, so that's the reduction half reaction. That's the one that we've circled over here. So which ions will be present in the half cell? Well, look at that equation. We've got ions of 3 plus becoming ions of 2 plus. It's not too often that we see one of these where it's ions just simply changing their charge and not actually precipitating or forming as ions even from metal. So in this case, we have iron 3 becoming iron 2. So we would need to have both of those ions present in the half cell. So 2 and 3, iron 2 and iron 3. And so our answer here is letter D. Now, just to kind of think about that, we don't often draw these out. So in that half cell, right, we would have iron 3 becoming iron 2. So we would load this half cell up with, say, iron 3 solution, iron 3 nitrate solution. Something like that, and you have a bunch of iron 3s in there. And this is just sort of for your knowledge. This isn't something you'd have to do on this particular question. But these iron 3s then would turn into iron 2s when this would be our cathode here, our cathode electrode, the actual wire. This would probably be a platinum wire or a piece of graphite. And then electrons, flowing here. So the electrons coming into this from the zinc half reaction, our electrons are flowing down into the wire and into that. And as those electrons come across this iron, the reaction will occur and simply change the charge of that ion from 3 plus to 2 plus. So the reaction happens sort of across the electrode. It doesn't adhere anything to the electrode. It doesn't lose anything from the electrode. That platinum wire is an inert metal, rather stable metal. Same thing for a chunk of graphite like you use in class for the Petri dish reactions, hopefully. And the electrons are simply being transferred out of that wire to the iron ions. It's not that we're having anything really with the platinum changing at all. It's just a conduit, literally, of the electrons. So just in terms of drawing it, we haven't drawn many like that, at least not this year. And so take a look at that as how we'd show the ions changing form in the cathode half cell. All right, let's look at the next ones. Coming down to the end here. 27 is real wordy. But it's talking about how they've got this clumsy scientist who perhaps lost the markings on his or her direct current power supply. So we've got a battery or an outside power supply. It could be a 9-volt battery, but we don't know which end is the positive and which end is the negative. So essentially, we have to identify that. What would be happening on each side? So if I've got my battery here, this is my positive and this is my negative, okay, we don't know which one's which, so we'd have to kind of try to figure it out. But let's just pretend that this is the case. Let's just try it this way and label it. So at the positive side, what would be going on? And then at the negative side, what would be going on? So there's a wire here, right? So this negative means electrons are being supplied. Electrons are flowing out through this wire. Electrons are flowing in toward the positive terminal this way. So electrons are being supplied by the wire on the right side of my picture, which makes that then, let's see, cathode is reduction and reduction is gain, right? So we're looking for a reduction half reaction that would be occurring over here. And over here we're looking for an oxidation half reaction. The oxidation reactions show the loss of electrons, and those electrons are lost, so to speak, through the wire toward the battery. And then they're out the other side and used on the other side. So what would happen with reduction in the scenario that they've given us? They've given us Ki solution, Ki solution in water. So what in that Ki can be reduced? Now you might look at that and say, well, the K, it's got a +1 charge, it could gain an electron, it could become potassium metal. But potassium's uber unstable, right, in water. So potassium metal can't just exist and like plate onto the end of the cathode in our reduction half cell here, or on the reduction side of this electrolytic cell. You can't plate out potassium out of a solution. In order for that to happen, we'd have to have molten salt, molten Ki, and then we could potentially plate out or form solid potassium. But in any other case, though, here, this won't work. Going from aqueous potassium ions to metal potassium, it can't happen. But in the water, we got a solution that can show reduction. So who can be reduced? We've already seen this in a previous question. Again, hydrogen can be reduced from hydrogen 1 plus to hydrogen gas. And in order to do that, it needs to take 2 electrons in, and out the other side are 2 hydroxide ions being formed. So that's the reaction that would occur at the positive or the negative terminal. Okay, so this is our negative terminal, and our evidence here would be a gas. So at the negative terminal, we would have a gas. Well, we've got that here then. So a negative electrode, a gas would be evolved. Looks like we maybe have our answer, right? So let's see if we can maybe look what would happen at the other side. On the other side, oxidation-wise, we have iodide available from the Ki solution, and 2 iodides can lose 2 electrons to become iodine, releasing those electrons. And hopefully you saw this in the Petri dish demonstration too, that iodine then comes out as a yellowish, brownish sort of solid, and if it's in a solution, it might slightly dissolve and sort of make sort of a faint yellowish, brownish solution area around the end of that little electrode. And so this is that yellow-brown iodine that we see. And maybe you've seen it if you've ever had like a surgical prep scrub on your skin or something where they're going to make an incision or insert a syringe or rather a needle. So yellow-brown would be the evidence here. And wait a second, now I see brown in this option C, but it says near the negative, oops, the heck. It says near the negative electrode. Well, that's not the case, right? This is negative electrode. We're at the positive electrode. So this is out because it's not the negative electrode that's happening. And then D says a metal will be deposited in the positive electrode. Well, they're kind of hinting at that idea of the potassium where that would be a metal, but that, even if it was happening, would not be at the positive electrode. It would be at the negative side, but we ruled it out. So that's not happening. A gas would be evolved. We already showed here that probably not. We're looking at a yellow-brown solid being formed at the positive electrode. So gas at the negative electrode, most likely scenario there. All right. Now, before we leave that one, you might argue, I suppose, that water could be oxidized at that positive electrode as well. The oxygen could be oxidized from the water. And then we'd actually get a gas at both terminals. Okay. But as far as our answers here, we know for sure that we're going to get a gas at the negative electrode because that's the only reaction that's favorable in these conditions at that electrode. So we'll go with B as a good answer, if not perhaps an amazingly good answer here. Maybe a better answer would be E, gases evolved at both electrodes potentially, because as we see in our demos in class, we're going to get that iodine over there at the positive terminal. We're probably also going to get some gases. All right. Which will make the largest voltage, assuming largest positive voltage here. Well, that's where you want to take the two extremes, right? You want to take the most positive one, which is this one, and then the most negative one and flip it. And if we did that, we'd get positive 1.665. We put those together and get a voltage of 2.4. That's the largest combination we can build from these 4 given half reactions. So we need 3 and 4. That's letter D. 29, it uses an equation that we saw in an earlier question. And it asks us to do something much simpler this time with it. Which of the following is true for the decomposition of peroxide? That's this reaction up here. So make sure you're looking at the right equation. That's the decomposition of hydrogen peroxide. And since it has a positive voltage, again, we're looking for positive voltage to mean it's favorable, so a negative delta G. So that rules out A and B. And a big K value because it's highly favorable. So a large K value would mean C is our answer for 29. All right, number 30. This is another one of those that can be balanced in half reaction form and is actually kind of like that one we saw with zinc earlier. So I'll do this one. If this is confusing to you, maybe just skip ahead a few seconds in the video to 31 and I can talk to you about this later. I don't believe this is going to be a must-have skill, but it's a nice handy skill if you've got it. So let's start out with magnesium because magnesium's becoming magnesium 2+ as our oxidation reaction and releasing 2 electrons. That one's balanced just as it is. And what that also tells me then is that all the rest of these pieces, NO3, NH4, hydrogen ion, and water, those are all going to be part of my other reaction because they're obviously not part of this one. So N is being reduced from 5+ in my nitrate to, on the other side, NH4, 3- in my NH4 ion. Okay. That's not neither here nor there just this second, though. So let's see if we can balance this one, again, with respect to atoms, and then with respect to charge. So nitrogens are balanced, one on either side. Oxygens, I have 3 on the left. I need 3 oxygens over here, and I get them by adding 3 waters. And then I have on the right side 6 hydrogens in my waters plus another 4 in my NH4 ammonium ion. So that's 10 hydrogens total. On the right side, I need to add those 10 hydrogens in on the left. And like before, we're going to balance this with respect to charge. Presently on the left side over here, I have 9 plus and only 1 plus over here. So like in the last one, we're going to add 8 electrons to this guy too to make that balance out. So now with respect to charge, the left side of my equation over here is a plus 1. 1 plus, pardon me for that glitch. And on the right side, it's a 1 plus as well. So now it's balanced with respect to charge. And like before, if we're going to put these together, we need our electrons to jive. So we're going to need to take this times 4 and times 4 and times 4. Get that like so. When we put these back together again, what will be the coefficient on our hydrogen ions? Okay. Now we think about looking at this. Can I imagine if I put all these together, would anything cancel? My electrons would cancel. Nothing else would cancel. And I can't reduce my coefficients, right? You want to be careful there because they want to know what's on the H. Well, this is a 10, but what if I could simplify it down, perhaps? Usually we would imagine cutting it in half to a 5 if we were reducing the equation. That's not even one of my choices. But I can't reduce if I put these pieces that are left here. If I put all these together into one big equation, I can't reduce it because I have some odd numbers. Right? I have a 1 here, I have a 1 here, I have a 3. So that's not going to reduce. And so this equation would have a 10 in front of the hydrogen ions on the coefficient for that. All right, let's look at 31. Which acts as the oxidizing agent? Again, who's being reduced? We've seen a question much like this before, permanganate. Again, this time permanganate shows manganese going from 7 plus to 4 plus. Okay, and that happens when you don't do this in an acidic environment especially. We're here in a basic environment because we have hydroxides being involved. In an acidic environment, you'll get to manganese 2 plus. In a basic environment, it typically stops at 4 plus and then forms this nasty manganese oxide, which is a visible precipitate. But trivial, we have an oxidizing agent is the thing being reduced, and the thing being reduced is manganese. What contains it then is the agent, and so that's the permanganate ion. Now, 32 has a typo in it, so if you've tried 32 with much frustration, I apologize. This is the first time I've used this particular question, and it's a little bit premature because I printed them or I offered them to you, and then I've got these typos. And I know that frustrates you, so I do apologize. But we've got a typo, and it's in choice B, which probably tells you that choice B is the right answer. But the thing is, they've got chromium here as plus 1 on the left side of the equation. This should be 2 plus, okay? Because 2 plus is becoming 3 plus. And that, of course, represents this second equation flipped. If we want to know which of these would be able to occur in aqueous solutions under standard conditions, we need to get a positive overall voltage. And so we need to flip our second equation to a positive 0.41. That would give us chromium 2 on the left, as is shown here. That would give us copper 2 on the left, which is shown here. It would also show us chromium 3 and copper metal on the right side, and I see chromium 3 and copper metal. Of course, the difference in these equations, the 2's, of course, come from the idea that we would need to double the chromium equation to get the electrons to cancel out. All right, 33. Half reaction occurring at the anode. We want to look for oxidation, so something being oxidized. I see iron going from iron to iron 3. So the reaction that's occurring then at the anode would be iron being oxidized by losing 3 electrons. That's letter B. Number 34. This is a solution, or rather a redox reaction in a basic environment. And I mentioned earlier we're not going to do any in basic environment. So the purposes of my video here, we're going to skip over 34. I can show you that one. It's not too much different from what we did earlier, but I'm not going to require it of everyone. It's a little bit of an older tool I don't believe you'll actually need. So if you want to learn about that because you're a sharp cookie and you want to learn everything, talk to me. I'm happy to show it to you. I kind of think these are fun to do, but they're not something that everyone has to do anymore. So save the time. Final question of the packet, finally. Whew, we've made it. Which substance is the reducing agent? That's who's being oxidized, right? This is a reaction equation showing what's going on in your car battery. a lead acid battery, as in your car. Most common batteries still found in typical vehicles as of today. There's our lead, there's our acid. It's really concentrated sulfuric acid in your car battery, which is why you don't want to putz around with it or open it or have it break open on you, because there's acid in there. And it's this redox reaction that you see here that results in the flow of electrons that powers your vehicle in terms of voltage for your starter and your radio and all the lights and everything. So this reaction is very important. It looks kind of benign, but man, it's important. So the reducing agent is who is being oxidized. Well, here's lead 0. Here's lead 2. Right like that. Now we actually have lead also 4 plus going to 2 plus. So lead in both is both being reduced from 4 plus to 2 plus and being oxidized from 0 to 2 plus. So it's actually lead that's doing both things. The reducing agent is the species who's being oxidized, and so that's this guy right here. We're looking at A as our choice. The oxidizing agent would be the lead oxide. The sulfuric acid in this case is the environment provider. It's really just providing a lot of hydrogens for this reaction to occur, more so than it's really being involved in terms of the redox itself. So there we have it, guys. Thanks for listening so much. And there's a lot here. Hopefully, if you have any more questions, we'll have a chance to talk. And until I talk to you again, thanks for listening and keep up the great work.